Hey everyone, and welcome to this explainer. We tend to look out at the world, at towering mountains, massive, deep valleys, and we just kind of assume they're permanent fixtures, right? But the reality is actually completely different. Literally right beneath our feet, the Himalayas are still pushing upward, while entire coastlines are being chewed away by the sea. It is this relentless, epic tug-of-war of massive geological forces that are constantly building up and tearing down the planet. So let's dive right in and uncover the incredible mechanics behind these geomorphic processes.
So our starting point here is a pretty fundamental mystery. Why is the surface of the Earth so uneven? Think about it. Why aren't we just living on a perfectly smooth, spherical billiard ball? Well, the answer is that the Earth's crust is incredibly dynamic. It's been shifting vertically and horizontally for billions of years, and it's absolutely still doing it today. All this unevenness, it's the physical footprint of an ongoing war between two vastly different types of forces. Let's meet the combatants.
We've essentially got two main competitors in this geological battlefield. Over in one corner, we have the endogenic forces. Think of these as our land builders. They originate deep inside the Earth, pushing the crust upward to create massive relief, your mountains, your plateaus. And in the opposing corner, exogenic forces. These guys operate from the outside, mostly from the atmosphere above, acting as the land sculptors. They are constantly grinding down those high elevations and filling in the deep basins. And honestly, as long as these two keep fighting, our Earth's surface is going to stay fiercely uneven.
All right, let's look a little closer at part one, endogenic forces, our land builders. Now, you might be wondering, where does the sheer power to literally lift an entire mountain range actually come from? Well, this incredible land-building muscle is fueled by immense energy buried deep down within the Earth's core. It's mostly generated by radioactivity, mixed with rotational and tidal friction, plus the leftover primordial heat from when the planet was first formed. All this intense internal heat flow creates unimaginable physical stress on the crust above it, which eventually leads to massive geological events.
All of these processes that move or elevate the crust get lumped under one pretty heavy academic term: diastrophism. But let's break that down into four clear, easy-to-digest actions. First, you have orogenic processes. This is severe folding of the crust, basically mountain building. Second is heterogenic processes. These are massive forces that slowly warp or uplift huge chunks of continents. Third, earthquakes, which cause relatively minor but very sudden violent local movements. And finally, plate tectonics, the horizontal shifting of massive crustal plates. So, those are the builders. But as we know, nature always demands balance.
Which naturally brings us to part two, exogenic forces, the land sculptors.
The ultimate goal of these exogenic forces can really be summed up in one crucial word: denudation. It literally means to strip off or uncover. It's the grand umbrella term for all the ways the Earth's surface gets worn away, encompassing weathering, mass wasting, erosion, and transportation. If you put them all together, they act like a giant planetary sander, slowly but very inevitably smoothing out all those rugged edges the internal forces just finished building up.
But here's a question. If the Earth's internal heat builds the mountains, what exactly powers this planetary sander? The ultimate energy sources are actually twofold. First up is the sun. The sun's energy drives our atmosphere, creating the weather, fueling the water cycle, and setting the stage for all our different climates. And second, the relentless, inescapable pull of gravity. Gravity doesn't just pull rain down from the sky, it pulls literally all Earth materials down slopes. Without gravity and the steep slopes created by tectonic forces, nothing would move. And if nothing moves, you get no erosion.
Let's zoom in on part three, weathering, and how things actually break down.
Weathering is what we call an in situ or on-site process. It weakens rocks right where they sit. And there are three main ways this happens. Chemical weathering uses water, oxygen, and natural acids to literally dissolve minerals. It's a lot like rust eating away at a car. Then there's physical or mechanical weathering. This breaks rocks apart through sheer applied force, like the massive pressure of thermal expansion. As temperatures fluctuate, it acts like a slow-motion jackhammer. Finally, biological weathering. Think of plant roots wedging themselves into tiny crevices or burrowing creatures constantly exposing fresh rock to further attack.
And climate? Climate plays a massive, massive role in dictating exactly how these processes play out. Take a region like the tundra, for example. There, precipitation and temperatures are super low, so the weathered layer of Earth, what we call the mantle, is incredibly shallow. But as you move into savanna and tropical forest zones, heat and rainfall absolutely spike. When that happens, the depth of chemical alteration plunges deep, deep into the Earth, creating massive, thick zones of clay. So weathering isn't uniform, it's highly dependent on the local climate.
Because of this, the results of these forces can look wildly different depending on where you are. On one hand, you have exfoliation. It's this quiet, creeping structural fatigue where temperature changes cause curved sheets of rock to slowly flake off over decades, almost like an onion peeling. But contrast that slow burn with the sudden devastation of a massive landslide scar. That is what happens when weathering weakens the rock so much that gravity suddenly and violently takes complete control.
That perfectly tees up Part 4, mass movements, the point where gravity ultimately wins.
Mass movements are a really unique phenomenon. It's the transfer of rock debris down a slope under the direct influence of gravity. Now, why is that distinction so important? Well, because unlike regular erosion, mass movements do not need a transporting medium. They don't need running water or a creeping glacier or heavy winds to carry the debris. Sure, there might be water mixed in there, but gravity itself is the sole engine doing all the heavy lifting.
Earth materials generally have their own natural resistance. They can hold themselves up, but they finally yield when an external force just tips the scales. And there are several critical triggers that can cause this. It could be the removal of support from below, like when a river cuts into a steep bank. Earthquakes, or even artificial explosions, can quickly shake material loose. Heavy rainfall can completely saturate the soil, basically acting as a giant lubricant. And, unfortunately, very commonly, it's the indiscriminate removal of natural vegetation. When we rip out the plant roots, we're removing the very things holding that fragile soil together.
To picture how this actually works, take a mechanical slump, for example. When the Earth finally gives way, it doesn't just tumble randomly down the hill. In a true slump, the whole block of rock and debris slips and actually rotates backwards with respect to the slope as it falls. It's a very specific, almost graceful structural collapse. And understanding these precise mechanics is absolutely vital if you want to predict and manage these really dangerous mass movements. So what does this all mean for us? Let's move to Part 5, protecting our fragile surface. You see, the Earth's surface is incredibly sensitive, and yet we depend entirely on this thin, weathered crust for our survival. Almost all of the surface we live on was shaped slowly over hundreds of thousands of years. But human activities today, things like intense agriculture, rapid deforestation, massive construction, they basically act like exogenic forces on fast forward. We are rapidly accelerating the Earth's natural degradation, completely disrupting a delicate geological balance that took millennia to establish. Which leaves us with a final, really provocative question to think about. How can we use the Earth's surface without ruining its potential for the future? We obviously have to use the Earth to survive. But by truly understanding these forces, knowing whether a slope is prone to slumping or how deeply a specific climate weathers its bedrock, we can actually build and farm in ways that respect these epic geomorphic processes. Thanks so much for joining me on this explainer, and remember, always keep questioning the ground beneath your feet.